Okay, thank you. Hello, everyone. I guess it's good to have a good number of people to start. So yeah, first of all, thank you very much for joining today's seminar. So today with great pleasure, we have Dr. Colin Zarzycki. I hope I pronounced this.
Yeah, Zarzycki, but we've changed it a lot if we came back from Poland, so it's okay.
Right, so so Colin is now is an assistant professor of meteorology and climate dynamics at Penn State, and so Colin has a degree from Cornell and the University of Illinois (UIUC), and also a PhD from University of Michigan Ann Arbor, and he's now leading a group on extreme weather and climate at Penn State, and definitely climate modeling is, I guess, one of your main research approaches. Yeah.
So,
Okay. Yeah. So today, I guess Colin will talk about projecting impact and communicating risk with high resolution climate storyline simulations. Yes. And before we start, so Colin doesn't mind if you have a question and to ask, but I just to gently remind you that if this is a free question, yes, sure, we just ask. But if this is the thing you want a longer or more comprehensive answer, maybe just stick it to the end. Yeah, and we start. The stage is yours.
sounds good. Well, thank you for the invitation to come. It's been great to meet with some folks. I know I'm meeting with some folks afterwards. So yeah. I want to share some results of some things that we've worked on the last couple of years, really focusing on impacts and risk. And what we're going to be using is climate models, in particular high resolution climate models, as a tool to be able to do this. So a couple things before we go ahead and get started. I'm giving a presentation, but I do want to acknowledge that most of this work is a combination of two master's theses, one by my student Corinne, who is now working in Marty Ralph's fiefdom or whatever out at Scripps. And then Abby Pettit, who did some work with me and has now moved on. She's at the National Weather Service in San Angelo, Texas. So if you're ever driving through the Texas Panhandle and you need to stop in the National Weather Service, by all means, say hi. She'll probably be like, why are you here? But, and then our funding agencies, I want to highlight that most of this work is being done through the Department of Energy under a project called Paper Facets. And then some of this work is also funded by the National Science Foundation through Project Rygen, which I'll share a slide on later. Might be useful for some of the grad students who like working in Python. Okay, so one of the things I saw someone give a presentation recently at Penn State, I was like, that was a good idea, is to give kind of a really quick 30-second crash course on where I came from. So I grew up in a small town in Connecticut, Torrington, Connecticut. I was one of the kids that watched the Weather Channel. That's how I got into this. And I always tell my students, like, this was before you could just log on to the internet and see what the latest Hurricane Center fix was. So I used to turn on the Weather Channel. It was 10 minutes to the hour. The tropical update, Dr. John Hope at the time, unfortunately, has since passed away. But this was my introduction into meteorology. I then went to do my undergrad at Cornell University. Not too far away from here. And I know we had some Cornell connections. I then decided, so my degree was in meteorology. I said, I'm not really sure I like this. I'm going to do meteorology for the rest of my life. So I wanted to go. I got a degree in civil and environmental engineering from the University of Illinois. So lived out in the cornfields of Big Ten school number 1. Then I decided, yeah, okay, maybe I did like this meteorology thing. So I'm going to go back and get my PhD at the University of Michigan. I like to tell people that this is maybe the only Jeopardy answer I'm going to be part of, but Michigan still, to this day, holds the record for the largest college football game. It was a night game against Notre Dame where I think they like shipped in some extra seats to put some folding chairs down on the field or something. So then after Michigan, I went out to NCAR for 5.5 years, where I first was an ASP postdoctoral fellow at the National Center for Atmospheric Research in Boulder. My first day was September 1st, 2014. This is what the weather was out there. You would think September in Boulder, everyone told me it's going to be sunny. Boulder, it's great, it's beautiful. And it snowed, which I still thought was kind of crazy, but I really loved working there. And then about 5 years ago, I moved to Penn State, where I'm at my current position as assistant professor. So Big Ten school number 3, if you're counting. I like this because this is an aerial view. Most everyone is going to be focused on Beaver Stadium and our Bryce Jordan Arena, the basketball arena, and meteorology is kind of periphery of the picture, but we are still in the picture of all of like the athletic, materials that people show. Okay, so enough about where I came from. So what does my group study? So we're very interested in studying climate extremes. And so the motivation behind this is if we think about how climate change or variability is going to affect the populace, affect society, these events, these kind of discrete phenomena are going to be disproportionate or have a disproportionate effect on health and welfare if they satisfy really two criteria. One is they have to be rare. So they have to be something that we don't really experience in our day-to-day or even our year-to-year lives. And they also have to be severe. So they can be anomalous, but they also have to be anomalous in a way that has some sort of impact. So when my group thinks about extremes, we generally think about a group of what we would consider weather extremes, although it's maybe not necessarily always in a traditional kind of synoptic or mesoscale sense. But when we think of extremes, what I like to mention, or like we study things like tropical and extratropical cyclones, severe convective weather outbreaks, floods, droughts and wildfires, heat waves, and cold snaps. And then one of the other challenges of studying climate extremes is these are generally fairly in the grand scheme of things, short-lived phenomena. They occur over time scales that we're thinking of like hours to days. So if the climate mean over long periods of time, like the monthly mean or the annual mean shifts, it maybe implies what's going on at these short time scales, but it's really hard to kind of ascertain without understanding how that distribution of events is going to change. What is happening with these kind of, again, small scale in both time and space extremes. And so one of the ways we're interested in studying these climate extremes is through this idea that is known as storylines. And this is something that's gotten very popular, I would say, over the last 5 or 6 years. The paper that most people generally cite is from Ted Shepard in 2018. But there have been people that have kind of on and off been thinking about this the last couple of decades. And the idea is, how do we communicate climate change and climate risk with people that are not climate experts? And in this paper, Ted Shepard lays out this definition that we can communicate these risks to this idea of storylines, which is the ability to tell people, hey, these are some of the risks you might experience, and we need to do it in a way that is credible so that we physically have a reason to understand why these risks may occur and why they may change, but also so that it is understandable, so that if you're just some person who may be experiencing climate risk, it's something that you can distill and also use something that people can make decisions on or maybe change behaviors in a way that make them more resilient or protect human health. So this aside, hopefully it's pretty self-explanatory why we might be interested in this from a societal perspective. What is my group particularly interested in? And the idea is I'm a modeler. I'm an Earth system modeler. That was my classical training, and that's what I spent a lot of time at NCAR doing. I want to ask the question, can we leverage high-resolution Earth system models to gain some sort of actual insight and understanding regarding climate extremes in the climate system? So I'm going to kind of give 2 highlights of use cases today. And again, this first one here is Corinne's thesis, and the second one here is Abby's thesis. But the first thing I want to talk about is what I would consider synthetic events that are mined and downscaled from high resolution global. It's a bit of a mouthful, but let's work our way through it. So like I said, climate events, we already have this. Disproportionately affect health and welfare if they're rare. I want to focus on this rarity standpoint. And, people that I interact with, stakeholders, they're always trying to protect against these kind of extremes. You want to build up infrastructure, you want to develop evacuation routes, you want to kind of have this in your arsenal so that if there was to be an extreme event, that you could respond in a way that protects as many lives and property as possible. But the one thing I want to emphasize is that our historical record is quite limited. So a lot of times what we'll do is we'll start trying to build this resilience based off of what has happened over kind of our recorded history, which in many cases at best may only be something like 100 years. So how do climate scientists historically get around this? One is we can use statistics, so things like generalized extreme value. or other kind of distributions. But also the way that I'm most interested in is using some sort of dynamical model. So again, trying to predict what is going on with the system. And then I did pull this from one of my modeling classes, but again, just so we're all on the same page, is what is the goal of a climate model or an Earth system model? And the idea is we have the planet Earth here, which I've stolen one of NASA's nice blue marble images. And we also have these equations that we know from our dynamics classes that in a continuum space govern what is going on in the atmosphere. And essentially what we're going to say is, I do not have the capacity to kind of simulate the continuum of the Earth system. But what I can do is I can discretize, in this case, the planet into numerous grid boxes, and I can recast these continuous equations in this numerically discretized form, and essentially just put this into a lot of computer code and create these models that predict what's going on in the system. And this is just kind of a zoom in of what's going on. But the one thing I want to draw attention to is that we break up the planet into these like little tiles. And so in this case, spatially delta X and delta Y. And when people talk about things like model resolution, this is generally what they're referring to. Is how big or how small are these grid boxes? I think we could actually get into a semantics argument. I would prefer to not call these individual grid boxes resolution, because that is not fundamentally the scale the model is actually resolving, but really this is the grid spacing. In principle, people use these terms kind of interchangeably, whereas high resolution means smaller grid boxes, low resolution means coarser or larger grid boxes. So why on earth is model resolution important to us as climate modelers? Well, so this is just kind of one quick example that I think really highlights kind of, especially when you're trying to get at some of these climate extremes, what making these grid boxes smaller can actually buy you. So this is a particular phenomena that was simulated in one of these Earth system models, and I've simulated at 4-degree grid spacing. So each of these boxes is roughly 4 by 4 degrees. It's roughly 400 kilometers or so. This is pretty coarse for what we would consider anything, maybe a paleoclimate model would kind of fall under this grid spacing. But now we'll move a couple orders of magnitude, or not a couple orders of magnitude, but a couple doublings of grid spacing or halvings of grid spacing down. These are what, if you were to go online and download climate model data from the CMIP archive from the Earth System Grid Federation website, if you hear people talk about the IPCC class of models, these are the grid spacings that those models are talking about, order of 100 to 250 kilometer grid boxes. And maybe you can start to see what dynamical structure is kind of coming out of this particular graphic. But it's really when I move to these much, much finer grid boxes. Now, this is actually getting down to what we would consider operational numerical weather prediction grid spacings down at 1/8 degrees. So this is roughly 14 kilometers or so. That we see that there's actually a simulated satellite image of Hurricane Sandy. But the idea I want to emphasize is that across this spectrum of grid spacing, there is a lot of improvement that can be gained from pushing these grid boxes to smaller and smaller scales. So the important take home here is that as resolution goes up, as the grid spacing goes down, we get a better representation of kind of small scale features, transient eddies, large land surface processes. Actually, a big one here is topography. I'm not going to talk about it, but I have a lot of colleagues in the Western US that are pushing a lot of their models of this finer grid spacing to get better orographic forcing, things like that, or snowpack in the Sierra Nevada. But the thing I'm most interested in is extreme weather. So if we push this grid spacing down to finer scales, we can do a better job of simulating these extreme events that we see on a daily basis on, like, for example, weather. The one kind of thing that the average person, and I always end up getting asked this if I do like a media interview or something, is like, okay, but I don't understand. Like, if everyone's using this, why wouldn't we just use this to solve all of our problems? Well, numerically, it's important to note that this is very expensive. So each time I go down one halving of resolution or one halving grid spacing, I increase the cost of whatever model I'm using on a large supercomputer, let's say, by a factor of 8. So just to go from this box to this box, I've now added 64 times my computational cost. So this becomes a very expensive operation very, very quickly. And that's the main barrier to being able to get information from these grid spacings at these longer climate time scales. Okay, so My first example is going to focus on tropical cyclones, hurricanes. So we have this model intercomparison project called the high-res model intercomparison. High-res. All we really need to know right now is that if we push climate models to 25-kilometer grid space, our current computing capacity allows us to kind of run these simulations for order of like 30, 40, maybe 100 years if you're really ambitious. This is like what we would call really pushing the envelope right now of the operational. And in this plot here, I have from a paper by Malcolm Roberts in 2020, just a bunch of plots of tropical cyclone, like it's like a heat map, a density map, where on the y-axis we have latitude. So, and this is only focused, I think, on tropical cyclones in the North Atlantic, so storms that would impact us in the eastern US. Latitude on the y-axis, and on the x-axis we have pressure. So any storms that are kind of toward the left side of this plot, they would be considered like more intense storms, things like category 5, category 4, category 5 hurricanes. And I think that's what we're really going to focus on, this left-right spectrum. We could also talk about the north-south, but it's not so. Also relevant is down here in this corner, what I have outlined in blue is observations. Now, so all these red boxes, I should say, are models, observations now. What this is showing is that we have storms in observations that have surface pressures or intensity of these kind of Cat 4, Cat 5 types. So again, like you turn on the news and you hear someone talking about one of these major hurricanes. Those are the storms that are to the left end of the spectrum. They have lower surface pressure. What we find is that these climate models, well, if I look at the coloring of this distribution, I find that the coloring is actually fairly similar across all these boxes, even with observations. What that's telling us is that these climate models simulate tropical cyclones, but is not simulating the full intensity distribution. In particular, this extreme tail, most of these red boxes are pretty empty. There are a few models that seem to be doing a better job than others, but nothing is really matching the amount of the cells that are kind of on the left side in this blue box.
Colin?
Yeah.
Can I just ask you? The data you're using to populate the cells is satellite and all sorts of satellite and ground data.
So that's what's populating this here. So this is actually a manually curated data set from hurricane researchers, and they're using whatever information they have at their disposal. Satellite images, surface-based observations, models, any of that stuff. All of these other products, actually what we do is when you get the climate model output, you actually develop an algorithm that goes through and it mines the data based on a set of rules that you can define for a tropical cyclone. So that's the one gray area here, is that this is hand curated and these are kind of automatically developed. And I'm not going to actually get into this, but there's a lot of effort in this space right now focused on doing things like taking labels from observations from forecasters and applying like machine learning and artificial intelligence techniques to better get this storm statistics out.
And second question, when you talk about the cost increasing geometrically, is that because the models are essentially gigantic matrices of every cell interacting with every other cell?
The simplest way to explain the cost argument is that every time I have resolution, so if I keep the vertical grid spacing of the model the same, if I have resolution over a two-dimensional plane, I make 4 times the number of grid cells. And then there's in numerical methods an idea that you have a constraint on the time step you can march forward in time in one of these models. So what the models are really doing is like trying to predict another step forward and then, oh, here's the atmosphere, and then trying to predict another step forward. The CFL criterion, we have to cut that in half every time we double the model, or every time we have model grid spacing. So each time we do that, we have a number of cells problem, and we have a time step problem, number of how small that step has to be, and combine that gives it. Yeah. All right. So, the big take homes here. 25-kilometer models. There's a lot of evidence that they do a relatively good job of like the climatology and kind of the background statistics, but they do not do a very good job of storm intensity, particularly at the very high end. And these are the storms that we're most interested in from a societal perspective. So it's kind of like the 25-kilometer model it gives us the number, the statistics, but it doesn't quite give us that thing that everyone really wants, which is what is the risk of things that really can impact society. I'm not saying a weaker hurricane wouldn't impact society, but the ones that you see on the news are not really well represented by these 25 climate models. Okay, so if I want to make decisions on things like coastal resilience based off of the historical record, the problem is, so this plot here, let's back up one step. This plot here plots all of the landfalling tropical cyclones color-coded by their intensity at landfall over the historical record. So this is 40 years of data. You could go and probably find your most interesting hurricane. Hurricane Andrew is buried down here. Hurricane Katrina is over here. Hurricane Sandy is up here. The thing is, we only have 40 years of data. So you can look at this and you can say there's certain parts of regions that are susceptible to tropical cyclones, like the Gulf Coast, that most places along that coastline have experienced a tropical cyclone over the last 40 years. But there are other areas, in particular, this one that always stands out to me is kind of along the spine of northern Florida, like in the Jacksonville, Daytona Beach area, where historically we really actually haven't observed a very intense storm that we can measure, hold up as our benchmark event and plan against. I mean, it's very possible there are some sort of dynamic or climatic impact that protects this region from tropical cyclones. Seems more likely that we've just ended up with a 40-year observational period where we've kind of gotten lucky that nothing has really made a landfall there. And in some cases, I would also say that South Jersey is not necessarily a magnet for tropical cyclones, but we've had a couple that have made landfall in that region. None actually in the Delaware Bay. But the thing I wanted to point out is with these climate models, what we can do is we can go ahead and run an ensemble of simulations over the historical record. And we just said that we think the climate models do a pretty good job of simulating the statistics, the mean statistics, the frequency of tropical cyclones. It's the intensity that's really the problem. So what we did is we ran a 9-member ensemble. The exact specifics of this are not overly relevant, but we generated 270 years of data. And this is all using historical force over the last 40 years. So the best way to think about this is we've rerun the last 30 years 9 times. And each of these climate integrations is forced at the boundary with sea surface temperatures and also with solar insolation, greenhouse gases, so on and so forth. But it's allowed to generate its own internal meteorology. So it's generating its own internal synoptic weather patterns, mesoscale weather patterns, so on and so forth. And if I toggle back and forth, what the climate model provides me is essentially, if I trust the climate model, which that's the argument we're making, it provides me with a synthetic data set of historically plausible but unrealized tropical cyclones. And you see that with this ensemble approach, it allows us to fill in the gaps along these coastlines much better. I mean, you'll see, for example, like places that already have a lot of tropical cyclone landfalls just get a lot more tropical cyclone model, but places that previously did not have tropical cyclone landfalls that we think climatologically, it's not really a great physical reason. Suddenly the model does say that, yes, it is likely that we possibly could get cyclones in here. So we now have this kind of interesting, well, not interesting push-pull, but we have 2,841 total trajectories in these climate integrations at this finer grid spacing, which is about 8 times more than the historical record. So the idea is we have essentially 8 times more tropical cyclones we can game plan against. However, we know that there's a low bias in terms of the intensity and the structure of these tropical cyclones. So what happens if we push these tropical cyclones in these models to finer grid space? And that's what my student Corinne. So this is just a map of all those tracks. We use that algorithm I mentioned earlier. The algorithm goes in and mines the DIC model. So all of these tropical cyclones are not real tropical cyclones. They all came out of the 9-member ensemble. The exact specifics of it, not super important, but there's our 13,024 tracks. And then what we did is we had a group in South Florida, a group of South Florida stakeholders that's part of this Department of Energy project that are mostly interested in water resources, some building and emergency planner folks that are working with us. And essentially the idea is, you know, if we can generate this climate data, what would be useful for your decision-making process? So what I had, what Corinne did was she took the 13,024 tracks and she said, okay, I'm only going to consider tracks that are within 500 kilometers of Miami. So I'm just going to draw a little circle around Miami. I'm going to take only tracks that go in that region. Now I have 486. So still a lot of cyclones, but obviously much less than 13,000. We then got on a 3-hour Zoom call with this group of stakeholders. There was a group of about 6 stakeholders, if I recall correctly. And we essentially toggled through all of these different tropical cyclone outcomes. And we said, you know, if there were particular storms that kept you awake at night, like things that you would be concerned about, what would they look like? Maybe they haven't occurred before. But if you were to turn on, you know, you were to go to Tropical Tidbits and you were to look at a storm and you were to go, oh, that's not good. Like, what would these look like? And the 3 categories that we kind of narrowed in on in conjunction with the stakeholders were storms that make a landfall at or just south of the Miami metro area. That one's pretty self-explanatory. If it's just south of the metro area, that puts you in the maximum area for surge, given the wind direction of the cyclonic flow. A stalled or slow-moving tropical cyclone, so something that kind of sits over the same period, same location for a long period of time, as well as sequential events. So if they already had a high water table from maybe kind of a nothing burger storm, but then you had another one come through, that really kind of loads the dice for flooding. And for this pilot project, we essentially isolated 9 tracks that we wanted to look at. And so what our plan is going to be is based on the results we saw earlier. This 25-kilometer model does a good job with the statistics, not a good job with the intensity. But we also know from numerical weather prediction that if we really push the grid spacing down and get it down into the 1-kilometer range instead of the 25-kilometer range, that we do a much, much better job of simulating tropical cyclones, both from a structural perspective, but also just statistically. Like the National Hurricane Center has found that if they want to forecast intensity, what they do is they use these like 3-kilometer models. But as we talked about, these 3-kilometer models are incredibly expensive to run because of the grid spacing. So we can't just run, you know, 9-member, 30-year ensemble, you know, type of simulations with this grid spacing. So how can we sort of bring these high-resolution models close together with these kind of climatological ensembles? And so our plan is going to be to take the results from the 25-kilometer model. So take the 9 storm tracks from the synthetic data set that these stakeholders have piloted for us. And we're going to essentially reforecast them. We're going to pretend they're like initial conditions to a numerical weather prediction model, except we're going to use a 3-kilometer non-hydrostatic model. I'm not going to really get into the details. The idea is it's going to be exactly the same. Everything's going to be exactly the same except the model grid space. So therefore, we're going to call that ensemble of simulations, the parent simulations, and we're going to call these downscale runs the children, so the parent and the child. So it's a family. And one of the things I really like about this is a really a unified framework. The idea is we run the lower resolution model, which is a high resolution model, with the 25-kilometer model to get the statistics. And then we take that same model and we almost like put a magnifying glass on it. And we zoom in on individual storms and rerun them in the same model, just like we would run a numerical weather prediction. The one quick advertisement I will provide is we have a lot of infrastructure that allows you to do this within really 3 particular models. The NCAR CESM model, the NCAR MPAS-A model, and the DOE E3SM model. Is a software tool called BetaCast that allows you to do all sorts of cool initialization on different grids and different climate models. And I've spent a lot of time making it nameless, configurable. It's all written in fairly poor Bash and Python. But if anyone's interested, the GitHub is here. So we have some grad groups around the country using it. So if you're particularly interested, please follow them. Okay, so this is my game that I usually play at meetings at AGU. Is I have 6 tropical cyclones on this slide, and one of them is a model simulated tropical cyclone. So I don't know if we do 1, 2, 3, 4, 5, 6. I'm sure only like 4 of you are gonna put your hands up, but who wants to tell me what is the model simulated tropical cyclone of these 6 panels? Yeah, I see a lot of number 2s. You guys are exactly right. This is the 28-kilometer version of our model. So from that 1/4 degree simulation, one of the storms that's making landfall in South Florida. But the catch is, I like to tell people, is there are actually 2 simulated tropical cyclones on this plot. So again, outgoing long wave radiation. So if I get rid of that, the bottom left corner is also a simulated tropical cyclone, except this is using that child grid. And the big take home here is this kind of agrees with what we saw before, was that the 28-kilometer model, we can get hurricanes, but they look kind of blocky. They don't really look like what we would see in reality. But by pushing down to this kilometer grid spacing, if you look really closely, and I gave you guys these 5, I'm pretty sure everyone in this room would probably eventually say this is the model, but it would be harder just kind of taking a quick scan. So we really do think there is benefit in pushing these grid spacings down to kind of these single kilometer, pushing grid spacings down towards single kilometers with the idea of better capturing the dynamics of the tropics. Okay, one more piece of advertisement is one of the things I kind of haven't really talked too much about is a lot of these new models are on what are called unstructured meshes. So they're not on traditional latitude, longitude grids. One of the things we've discovered over time is there are not a lot of tools for actually doing analysis on unstructured grids. Usually what people do is they take model from these arbitrary grids, data, climate data, and they interpolate it to like a latitude, longitude grid, and then they use tools like NCO or X-ray to analyze it, or sorry, NCL or X-ray to analyze it. However, we have a project called Project Rygen, but most importantly, we're developing a GitHub repository Python package called UXray that allows you to work with unstructured model data. So both of these grids are not tiled in a latitude longitude fashion, they're just kind of arbitrary one-dimensional arrays, but we can make really cool visualizations using the software. So I promise the PI. Okay, so a couple quick notes because I want to wrap this up and move on to the last little bit of the presentation here. So one of the things the stakeholders did ask us for is before we actually provided them with those data from the 9 kind of synthetic trajectories we talked about, they said, hey, like, is there any value added for our metrics for things that we are interested in on the ground with the 3-kilometer model? So what we did is we picked 4 historical hurricanes, Ian, Irma, Isaac, apparently hurricanes are important for Florida, and then also Faye. And they said, hey, these are 4 that were really important, things that really maybe stressed our infrastructure, or, you know, in other words, things that just were kind of benchmarks that we use in our day-to-day planning. And so what we did is we ran those in the 28-kilometer grid. So again, the grid that generated the ensemble. We ran them with the child grid, that really high resolution 3-kilometer grid. And then we were able to get some 4-kilometer NextRad data from a couple groups in Florida that they actually quality controlled and stitched the mosaic together. So we can kind of compare what are these models doing in relation to ground truth. So essentially we're running real forecasts or real oncasts of these events. This is storm total precipitation. So things like yellows and oranges represent where you're getting into almost feet of rainfall. So that's a lot of rain. And then we also have maximum hourly precipitation plotted here. The one thing I just want to mention, and you'll see this more on the next slide, is if you look in the observations in the NextRad data, we see a lot of these kind of greens and yellows pop up talking about getting rates of 3, 4, 5, 6 inches or more per hour. So this is maximum hourly rate, if I didn't make that clear. If you look at this lower resolution run, you really don't see that, maybe a little bit of green here in this Ian hindcast. But when you look at these 3-kilometer models, I now see a lot more greens popping up and even a couple of yellows and stuff to see on this slide. So it's giving us some hint that the extreme rates are being better simulated in the 3-kilometer model. Okay, just some really quick statistics. To actually verify which model was superior, whether it was the 28-kilometer model or the 3-kilometer model, we did some KS statistical distribution tests over the cumulative distribution. The exact details of it, let's not worry too much about. The big take home is what are these colored boxes? And so on the left, we have the total precipitation for these 4 storms. On the right, we have the maximum hourly precipitation for the 4 storms. The color of the box indicates whether the low resolution model did better, the parent model, the child model did better, or they both did equally well. So anything that is blue means the parent wins. Anything that is this kind of like pink or purplish color means the child wins. And anything that has this kind of in-between color, you guys probably can't see it, but it's a checkerboard. That just means statistically there's no difference between the two models. And what we found was that for storm total precipitation, there really does not appear to be any value added moving from this parent paradigm to the child. So if what you're interested in is how much precipitation falls within a particular event, it's questionable as to whether there's a whole lot of benefit to me moving to this 3-kilometer frame. Where we do see a lot of benefit is when we go and compare to the NextRat data and we look at the maximum hourly rate. Across the board, the 3-kilometer model outperforms the 28-kilometer model. Remember, we've done no additional tuning or calibration of the model. All we've done is we've turned up the width. We've turned up the resolution on the model, reforecasted exactly the same event. And suddenly all this high frequency extreme information is better simulated in the 3-kilometer. So this is good. Stakeholders were like, that's great, like 3-kilometer data. If we're interested in high frequency precip extremes, things that occur like at less than 6 hours, things that are important for flash flooding, the example I always remember was like sewers and how much, there's a bunch of numbers on how much water per hour sewers can take. And obviously if it goes above that, it's not good for anyone. So, okay, high frequency precip, good. Let's see what happens with the synthetic tracks. So these are just the 9 storms that Corinne found. I've just overlaid both of the trajectories from the parent simulation and the child simulation. For the most part, the parent, this kind of parent-child paradigm gives us the same storm, which is really what we want. In a perfect world, you wouldn't be able to see a difference between the trajectories here. In reality, some of the trajectories deviate a little bit depending on which model you're using. Mostly I have this slide in here to keep people at AMS or AGU from yelling at me and telling me we need to run more ensembles. The answer is we know that. If we had an ensemble spread, we would probably do a lot better. So it's on the to-do list. But I briefly want to just talk a little bit about potential hydrologic value added from these simulations. So again, parent, child, so lower resolution, higher resolution, storm total. These are all synthetic events. None of these have occurred in the historical record. These are all plausible, what we would call gray swan events, things that we could expect and we should plan for, but thankfully haven't seen historically. I can do the same thing for the precip swap maps. Here, these are things that you could kind of look at, but really they're just for informative purposes. But the big take home I want to get to is this slide right here. Which just allows us to look at distributions of total precipitation, and then I'll show the maximum hourly precipitation on the right for these 9 storms. So these are just frequency distribution functions. But the thing I want to note is that Irma and Ian are kind of the 2 benchmark storms that these South Florida stakeholders have held up to us and said, these are things that are important for us. We make decisions based on these storms and how we respond to these storms. And in this climate data set, we've been able to produce at least 3 storms that have higher storm total rainfall than Irma and Ian. So what this is telling us is there is a potential risk in the present climate of getting storms that exceed the benchmarks that are being used by our stakeholders for planning purposes. You can also go to the maximum hourly precipitation rate and see the same response, except even kind of turbocharged. Which is, first we find that the parent simulation, which is this purple curve, sorry, I should have been more clear. The purple curve is the parent simulation, the blue is the child. In general, if you look at the maximum hourly precipitation rates, we get what we would have expected based on the previous results as the tail of the distribution kicks out to the right. But again, we've picked out multiple storms that exceed the benchmark intensity of these particular events. And so right now they have the data on hand for these particular storms, and they are using that gridded data to evaluate whether there is anything different in their operations that they can maybe do to plan for, again, these hypothetical gray swan events. So the super quick summary to this part. 3-kilometer models or 3-kilometer simulations using climate data, I think, is feasible today. There is a big effort to running 3-kilometer models globally. Generally, those are constrained by computational resources to around a couple months, maybe out to a year. But I think being able to marry these kind of long-running, lower resolution climate models and then these high-resolution targeted models can give us information about things like regional climate, process studies, or the things that I talked about today, detection and attribution, and storyline simulations, as well as synthetic events. The other thing I really want to emphasize is that these free-running climate models at 28 kilometers don't give us this tail risk in South Florida. But when we push the 3-kilometer models, we get storms that are very, very consistent with what we've observed. So I think we're very close to being able to use these models and these frameworks operationally in our hazard planning situations. Okay, so the last one I want to do, and I was actually kind of excited to talk about this one at the University of Delaware, is we are going to look at a counterfactual simulation of a historical extreme under different climate scenarios. So the one event that my student wanted to look at was this event known as, this type of event known as rain on snow events. Rain on snow events are a form of extreme called compound extremes, where you kind of have multiple things going on at once that kind of add together and turbocharge your extreme outcome. Rain on snow events are exactly what they sound like, where you have deep antecedent snowpack here in the eastern, well, in this case, in the eastern United States. You get a big rainfall event that comes over, drops a bunch of rain on the snowpack. You also get snowpack that melts. You get a double whammy. You release water that was stored in the snowpack. You also get water falling from the atmosphere. You get kind of this turbocharged flooding. The one thing I will quickly note is there's a bit of a misconception that it's actually the rain that falls into the snow that melts the snow. It's really not the case. It's usually meteorological conditions associated with the rain that causes the snow to melt, but they still get the name rain on the snow. The particular event we want to look at is the 1996 Mid-Atlantic rain on snow event in the Susquehanna River Basin. $5.3 billion in damages, 30 plus fatalities. This name probably looks familiar to some people in the department. So my student did a lot of digging on this. So she has all of these papers from the University of Delaware in her, probably somewhere in her file cabinets. So yeah, we're going to focus on the hydrology of the Susquehanna River Basin in this case. Okay, we're going to kind of do something similar. We're going to reforecast this event, kind of like we were reforecasting the tropical cyclones before, except now we're going to do a real world event. So this is not a synthetic event. This is something that actually occurred. We're using a different model. We're using the Department of Energy E3SM model. We're going to put a 14-kilometer grid over the United States. So we're going to kind of run this model like it's a numerical weather prediction model. And we're going to ask the question, can we reforecast the 1996 flood event? We're going to use this beta cast tool that I advertised before, but instead of being synthetic, hypothetic, randomly generated, cool looking tropical cyclones, we're going to just use AERIFY reanalysis, and we're going to try to make this look as real as possible to the historic. So the first thing that Abby went and did is we ran the model. So up here, this is the model evolution of the synoptic meteorology fields. Down here is the AERIFY reanalysis. So essentially our best guess of the historical recreation of this event. And what we find is that if you look at the synoptic meteorology, this evolution is generally similar between these two products. You get this kind of like inland running cyclone with this big warm air advection plume out in front. This warm air advection plume kind of streams into the northeastern United States, really ripens that snowpack. You put a lot of heat, a lot of energy flux into the snowpack. You get this frontal passage that comes through with very intense precipitation rates as that snow is melting, and then eventually the front passes through. But at that point, you've now had really intense precipitation and you've released multiple inches of snow water equivalent over the land surface. So Abby went and did some other things, like we went and did a lot of verification at individual stations. So she went and got a bunch of ASOS data, correlated temperature, humidity, wind speed, dew point. So the moral of the story is we get skill that is roughly comparable with an operational numerical weather prediction model. So we make the argument that this model for this study is what we call adequate for purpose. It means the model is not designed to look at this particular phenomenon, but that when confronted with this particular phenomenon, it gives results that are usable and consistent with the observation. So then what we're going to go and do is say, how would this 1996 flood event change under different levels of warming? The idea is maybe is this going to be different in the future? And so the approach we're going to apply is something that is commonly known as maybe a pseudo-global warming approach, thermodynamic global warming approach, fusion analysis, counterfactual exploration. The point I like to make here is there are a lot of different people that are trying to semantically stake claim to this type of analysis. At the end of the day, everyone's kind of doing the same thing. What we're going to do is reforecast this event, and we're going to add some sort of imposed warming and see how the event changes. The important thing I want to note is this is referred to as a conditional approach. So we are not stating anything about the frequency of occurrence of these type of synoptic events. All we are looking at is what are the processes that govern the evolution of this event, given the different climate kind of regime that this event is in. So to do this, we're going to use what's referred to as the delta calculation method. I won't get into the specifics of this, but essentially what we do is we run a climate model, a free running climate model. So this is not constrained by observational meteorology. This is what you would think of with a low resolution IPCC class model. We look at the state fields in some future year, like 2081. We subtract it from 1996. This was the year the event actually occurred in. And what that gives us is a fingerprint or a signal of what the warming looks like in 2081 as predicted by this model relative to the year of control, the year of the observation where the event occurred. And what we're going to do is we're going to take this fingerprint and then we're going to go take the initial conditions or the analysis from that 1996 flood, and then we are going to superimpose the two of them on, well, superimpose the warming onto the event. So the best way to think about this is we are reforecasting that flood event, but under different future climate conditions. Where do we get the future climate conditions? Well, we get them from a 40-member large ensemble of climate simulations. So I refer you to this paper by Jen Kay in 2015. And the one other thing I wanted to note that's kind of unique about this study is instead of using like a scenario, like you guys might be familiar with like RCP 85, RCP 45, what we're actually going to do is just take one scenario and we're going to look for warming. So which year does the global mean temperature exceed a certain threshold? And the idea here is that this is easier to communicate to non-experts. You know, we kind of remove us as climate scientists having to guess at what policy is going to look like. We say, hey, this is what the event would look like when you have 2 degrees of global warming. It's up to you, policymakers, how you want to get us to 2 degrees of global warming. That's above my pay grade, at least. But this is kind of what these events would look like in these different regimes. So you could think about this as like, not necessarily, don't think of this as like 2045, but the year that we achieve 2 degrees of warming in the global climate system. Okay, couple quick things. So these are just some hydrographs of the evolution of various parameters in the ensemble of ABBY simulations. I think the ones I just want to draw your attention to, well, so first of all, 2 meter temperature. As the colors of these lines get warmer, the atmosphere gets warmer. So this is kind of that bump you get with that warm air advection that out in front of the frontal passage. And you see that as we move from the control simulation, which is the hindcast, to these progressively warmer simulations where we add more and more of that warming signal, the warmth that's associated with that advection increases. This is the snow that is in the Susquehanna Basin, so the snow water equivalent. And what you see is that at initialization, the snow water equivalent decreases with warming, which makes sense. Some of the antecedent conditions in this very warmer world are actually not warm enough to produce snow that's on the ground. Although one thing I always like to point out to people is that even in this extraordinarily warm future world, in this particular era, we still did have a decent amount of snowpack. So it is not like snow is going to go to zero in any of these future simulations. Precipitation over here generally increases with warming. This follows roughly Clausius-Clapeyron. But I wanted to point out down here, surface runoff. This gives us a proxy for the amount of liquid water on the surface. So runoff is just kind of what is moving laterally across the surface. It's a combination of precipitation and rainfall. And what we find is that it increases for some warming levels and then eventually decreases and also shifts forward in time. And I have a better plot that shows that, I think, on a future slide. One thing I do quickly want to show is I have this kind of fancy movie. So this is stream flow in these model simulations. The reviewers pointed out we need to be very careful when analyzing stream flow. This is a fairly low resolution hydrologic model that is coupled to E3SM. But a couple things I want to know is that if you look at this 2-degree warming, we get increased amounts of stream flow. That's what the red represents relative to the control. But if I look at 4 degrees of warming in the evolution of stream flow, I see a small pulse of red followed by a larger pulse of blue. And again, for simplicity, red means we have more stream flow, blue means we have less stream flow. So we have kind of more flooding conditions here in the Susquehanna, and you can also see some delta over here. Over here, you get a brief pulse of red, but then a lot more blue. So you get not only a decrease in the eventual stream flow, but a bit of a timing shift, an increase in the flashiness of the flood event overall. But this is, to me, the big take home here, which is if you look this side, the 1996 event highlighted here in this, this black rectangle, the warming level is down here on the x-axis. So as you move from left to right, the atmosphere gets warmer. So here is temperature. This makes sense. The temperature of these simulations increases over the Susquehanna River Basin as you get warmer, and you could actually look and correspond these warming levels to roughly what we defined earlier. Precip also increases again, roughly talking about the precip. We are not differentiating whether this falls as snow or rain, but in this particular event, it's all rain. But what you find is that the change in, this is actually the change in snow water equivalent. There should be a delta here. So the amount of snow melt and the surface runoff have non-monotonic relationships with warmth. So interestingly, temperature goes up, precip goes up with warming. We think everything's getting worse with warming. But the melting of the snow, and in absolute sense, actually maximizes somewhere between 1 and 2 degrees of warming. And runoff seems to maximize around 1 degree of warming. So this would imply that there's some sort of tipping point for this particular event that leads to this nonlinear relationship. And then the last part of this is, well, what is contributing to that? So what we did is we went back and did a surface water budget. Not going to get into the, I do have an interpretation pop up here. Essentially, you can do a surface water budget of the land surface model, and you can look at all the different things that could either add water or subtract water from the land surface and figure out what is going on with this push-pull in these different warming simulations. So we did that across all the simulations. So we looked at things like what is snow melt and how is that contributing to surface water, what is going on with the soil water, things like evapotranspiration. Evapotranspiration in the Susquehanna River Basin in January, pretty much non-existent. But the big take-home interpretation is that the volume of the, what did I say? So the volume of the snow that is actually released from the snowpack is roughly similar with degrees of warming. So how much snow you actually melt off doesn't really increase a lot in the future. So you're actually not really getting, it's not like a 4-degree warming world releases twice the amount of water through the snowpack. So this was kind of surprising to us. We expected if there was snowpack, the warmer the world was, the more overall snow it would melt and the kind of the more flooding. And the other thing that was essentially worth noting, and I kind of buried the lead over here, is that at some point with enough warming, we actually thaw most of the soil in the Susquehanna River Basin. And what ends up happening is that even at higher warming levels, we melt all that snow, but instead of the snow running across the surface and into the Susquehanna River, for example, a lot of it now percolates through the, or is kind of into the thawed soil. And even in these warmer environments, the capacity of kind of the land surface to absorb that runoff before we get that ponding or that flowing into the river basin, the ability of that soil to uptake that water actually increases greatly. So yeah, unfrozen soil can uptake the water from both the snow and the rain. So at these warmer levels, you actually get less runoff and less stream flow because more of it is just going down. Anyway, I could probably talk all day about the interesting processes here. Like I said, the things that kind of really stood out are that these rain on snow events are pretty unique in that they result from multiple concurrent processes. The temperature and precip show this monotonic expected response. So this is kind of the thing that's pretty standard in like extreme literature, is that we see under future climates, things like heat waves, heat extremes, precipitation extremes. A lot of these things are increasing monotonically with warming. But there are these events, and this is just one particular example of an event, particularly these compound extremes, where you get these interesting nonlinear responses, whether you either get a positive or a negative feedback as a function of warming. And so what Abby found in these particular simulations is that if you take this 1996 event, and in this particular model, you reforecast it, you end up getting a worsening of the kind of on the ground risk as approximated by surface runoff, up until a certain warming level, and then past a warming level, you make the event far more flashy, but you also allow a lot of that water to go into the soil. And that probably is going to change what our societal or human response is like. One thing I kind of also didn't talk about is that she found that the timing of the peak runoff shifts earlier, again, that flashiness, which could be important. Okay, so last slide, I promise. These short simulations, what they do is they permit the Earth system models to be run at ultra high resolutions. I think that's really exciting. I also really think that these storyline approaches are quite interesting or quite useful for communicating what is going on with kind of climate and risk, because we can essentially give people something like, if we do this, then the event responds in this way. It really gives us this nice physical bridge to how these events might change in a way that is experiential for people. You know, people remember the 1996 flood event. People remember specific hurricanes. If you can communicate climate hazards around those events, my hope would be that we could have kind of more success in figuring out better ways to plan for things. Yeah, so I talked here about that, how it's more fruitful than probabilistic approaches. I think there's a lot of benefit here in terms of talking with experts, so things like water managers, but even media and policymakers and the general public. The last thing I wanted to finish with was our kind of hot off the press simulation, which is part of this Department of Energy project. We have also been creating synthetic storyline simulations for the Philadelphia region, looking at energy resilience. So what would one of these big storms look like if it struck South Jersey, the Philadelphia area? What would this look like from a power outage perspective? So this is not Hurricane Sandy. This is a synthetic hurricane that is run with that framework from before. So this is a total gray swan event. And then what we're doing is we're using the wind and precipitation fields from this storm to force an electricity model to tell us something about the fraction of county outages following this cycle. So the joke I generally make is that this model seems to be very aggressive in getting the power turned back on after the storm comes through. So all these colors represent fractional outage of the county. So you can see as like the storm makes landfall, all these counties are like 100% knocked out. I have to ask Julian exactly what's going on, because I don't know about you guys in my neck of the woods. If the power goes out, it does not come on 3 hours after the event passes through. But this, I think, is some really exciting frontier pushing work with this kind of merger of these downscaled simulations and these kind of storylines. So with that, I apologize for rambling a little long, but I really appreciate everyone staying here on a Friday and happy to answer any questions.
Right, so do we have questions? I'm looking through the Zoom.
Okay.
I have just a couple. One of them is about the last one. Did you guys look at dew point at all for the 96 flood and how that changed in the model? Because one of the things we found in that paper was that a lot of the latent heat flux from the, essentially condensation onto the snowpack really helped to melt that pack fast. So I just wondered if you guys took a look at dew point at all.
So I have to go back. So it's all buried in the supplemental information in poor Abby's thesis. So we did look at relative humidity dew pack. We also did, the nice thing with the models is you can also look at the energy fluxes into or out of the snowpack. I can't recall, I vaguely remember the fluxes themselves being relatively, like, they're impactful for the event evolution itself, but they actually remain relatively static as a function of warming, or at least relatively static relative to some of these other things. but without. Follow up with me and I will go dig up the actual results from the model.
I just wondered, and the other thing is when, back to the tropical cyclones. When you were having the parent and the children, so you were running the same model, but just increasing the resolution to, and so my question is how did you change the convective parameterization? Because that would be really important for the hourly range.
Yeah, those atmospheric scientists, you're always, no, so I actually buried, so they're identical except for two things. So one is we actually use a different dynamical core for the high resolution model. It's a non-hydrostatic dynamical core. The lower resolution is hydrostatic. The other thing we do with the 3 kilometer models is we turn off the deep convective parameterization. So we are actually running with what I would argue is some people would call that convective resolving. I do not argue that it's convective resolving because I do not look outside and see 3 kilometer cumulonimbus towers everywhere. But we are not running with the deep convective scheme at that resolution. That's actually a very interesting discussion point in our field right now. I would say the prevailing theory has been that convection needs to be parameterized up until around 3 to 5 kilometer grid spacing. ECMWF have found with their operational models that at 10 kilometer grid spacing, they actually get better global scale when they turn off deep convection, which to me implies that our convective parameterizations of some of these grid spacings may be doing more harm than good. But I think that's a totally open research question. But I did not mention on the slide, we do turn off deep convection.
Thanks.
Yep.
Any other questions?
Regarding the stakeholder engagement slide, would you like walk us through how the people responded and all? And you know, as this more of a social scientist, human geographer, I'm particularly interested in that.
Yeah, so it's yeah, I don't have like I should put out a little Zoom thing. So the way this actually works is we have a couple social scientists that work with us from the University of California, Berkeley, and they serve as the interface between the scientific arm of this project and then stakeholders that have kind of, it's a combination of stakeholders that scientists have already engaged with, as well as stakeholders that have kind of been entrained in the project through the Department of Energy or through these other kind of sectors. And essentially what we do is we hold quarterly meetings with them where both one of the stakeholders and one of the scientists kind of will present, but then we hold these ad hoc meetings where if we have a particular project in mind, the idea is to gain as much stakeholder insight in terms of, you know, which research, you know, the idea is we get a research project to like 50% fleshed out, and then we say, okay, we have these 3 different paths we can go down. What are the paths of interest? And that's where we went, you know, we wanted to do this downscaling approach and really stress test these models. But we wanted to do so, we wanted to use these computer cycles in a way that we thought that the data would then be useful for someone else downstream. So we got them on a call, we proposed and said, I gave them like a brief presentation that said, this is what we can do. Before we go ahead and run these 9 storms, that's our capacity. What are the 9 storms of this data set that you think you might be able to use in your operations? And then this group of 3, 4, 5, we actually, over the course of an hour or two, kind of narrowed in on these particular events that are relevant. So that's currently what our level of engagement is. The Department of Energy is very careful to remind us we are not a data generation agency, so that when we engage with the stakeholders, it has to be co-production. It has to be things that are scientifically interesting, but also things that are relevant for stakeholders. So trying to find that intersection is a bit like threading a needle sometimes.
All right. Yes, Christina, there's a question before you.
Just wondering, are there any differences between the hydrostatic and the non-hydrostatic?
Yeah, so the main difference, the one difference is the grid tiling is a little the same, it's a little bit different. But the real fundamental difference is the non-hydrostatic model includes a predictive equation for vertical velocity. So to be honest, if you run the non-hydrostatic model at the grid spacing of the hydrostatic model, you don't really get a difference. But if you run the hydrostatic model at the grid spacing of the non-hydrostatic model, you get updrafts that are too anomalously strong because they're only governed by horizontal convergence and divergence. So you don't have the pressure effects of the vertical velocity. But technically, from like a Navier-Stokes equation standpoint, that's the key difference. is whether we predict W, the vertical velocity, or whether we diagnose it from the predicted U.
These runs over a flat terrain, or do you have to follow?
So there is topography in this, although for these runs, well, so this run actually, there's, yeah, so all these are real world runs, we have topography. To be frank, like the Florida runs don't really stress test the topography part of the code. Florida's, I don't know, they might say they have topography, they really don't. It's really like a flat swamp in a model, but yeah. So, there is a group out at, again, out at Lawrence Berkeley that is using this model to look at terrain effects. And I'll be honest, I haven't looked too closely at their results, but they are using the non-hydrostatic model for those questions. Yes.
I don't know exactly what I'm gonna ask you, so it's more like brainstorming, right?
Yeah.
But it's about the idea that, oh, increase the resolution and everything will be fine.
Mhm.
And even your results show that that's not the case, right? Especially for the total accumulated precipitation, which is remarkably similar when you have the parent 25 km resolution one and the child higher resolution ones. But then when you look at the maximum intensity rate, it's so much better done with the high resolution one, and it's always under predicted with the coarse resolution one.
Yeah.
But yet the totals are the same.
Yeah.
So the totals are the same, but then the maximum rate is higher for the high resolution one. So somewhere in there, there's a shape of the distribution that is misrepresented in the coarse resolution one.
Yeah.
So I guess what I'm trying to say is that it sounds like you've got to correct something in the output of the coarse resolution run. And it will be so much quicker to run in the freaking 3 km run, and it will be, because the total is the same, you just
Yep. So you
pump it
are,
up here and lower it down at the edges or something like that.
so you are not at all wrong in terms of what, I mean, I have one grad student who is essentially trying to statistically downscale a lot of these models with machine learning techniques. And I think that is an interesting avenue. I mean, this kind of stuff has been historically done in the NWP community for quite a while in terms of taking course data and being like, the distribution doesn't look great, but the macro scale looks fine. So maybe we just need to massage the distribution and get the statistics right. The other very interesting thing in my mind is this also leads a lot, like what it also seems to be saying is that, there's kind of like an event scale control on the amount of precipitation, but how efficiently that precipitation is generated throughout the event seems to have a bit of a distribution. And from a thermodynamic perspective, this also gives us some idea that there may be ways to improve the parameterization in the low resolution model to better match the resolution.
And I like that idea better than just saying, oh, machine learning should give me the
solve
answer. Because there's gotta be something physical that is not being reproduced correctly in the parameterization. So
there is
that's really interesting.
Yeah, no, so there's an initiative right now called the Diamond Initiative, which I can never remember what the Diamond stands for, but dynamics something. And their idea is they're running the short-term 3 km global convective permitting simulations. And what their hypothesis is that if you do better, if let's say that you trust that the model is doing a good job, you're simulating the tropical circulation better with a 3 km model than a 25 km model, we can't run a climate simulation. But what we can do is we can use that 3 km model to build better parameterizations for the 25 km model. So whether that actually comes to fruition, I don't know, but there's been a lot of, Bjorn Stevens has been leading this effort, a lot of effort put into that idea of not just using the high resolution models to make pretty movies and results, but also using them to teach us something about them.
No, I really like this effort, because in my experience, there's a zone where, yeah, you improve the resolution, you refine the resolution, you get better results, but then there's a plateau inevitably, because at one point the cost of all these additional initial information that you have to provide at very high resolution, and it's not worth it, and I feel like we are right there.
There are many model biases that resolution does not just get rid of. They're just baked into the solution. So I always tell people resolution is not a silver bullet. Maybe with topography, but most other things it's not.
Right. Yeah, one last question.
Yeah, just one word. But here we're dealing with winds too, with this last example. I just wondered, between the 3 km and the 28 km grid spacings, how do the winds change?
So that, I do have a backup slide probably somewhere, but it's probably not super illustrative. The winds had less of a change across the resolutions. The one thing that does concern me a little, not concern me, but I have another student actually looking at boundary layer turbulence in models and has found that the representation of things like the surface wind are very sensitive to how we treat boundary layer fluxes, surface layer. And so we actually did get a slight kind of flattening of the wind distribution, so the tail kicked out a little bit, but the tail itself, we did not get the same signal we got in precip. So the way you could think about it is the winds looked actually very similar between the two. I'm careful to note that in general, we actually underpredicted winds though for the Cat 5 hurricanes with historical record with both models. So I would probably think that we would want to do more calibration of the wind if that was the particular thing. And that's, to be honest, the same here. This is really a proof of concept. No one is actually, well, like I said, I don't really trust this outage model to begin with myself. But mostly we were trying to see if we can build an infrastructure that develops this model pipeline. I would assume if this were to ever be used, or if people wanted to use this, we would probably do a lot more work on the verification side of things before. Well, I would hope that people wouldn't make decisions without that verification. I'm not that, so.
Perfect. And yeah, I don't see any question online except the thank you comments.
No.
So yeah, and with that, before we leave, maybe we give another round of first party.
Thanks for coming.
We've got, yeah, I just put it on, yeah, don't worry. Was there a question? Thank you for the presentation, and we could get a copy, yeah, we will, yeah, it will be recorded, well, we will put it on the YouTube channel.
That's perfect.
I also, I don't think there's any top secret slides. I've given this, part of this presentation, AGO, like, I'm fine also sharing. Okay.